Okay, in this lecture we're going to do something that is called the integral test. And it goes like this. If you have a series like this that it goes from n to infinity and you have an integral f of x dx that goes from n to infinity, as long as this function is equals to an for positive integers and f is continuous, decreasing and positive, then both the series and integral converge or diverge. This is called the integral test. So I'm gonna show that this series diverges by the integral test. I'm just gonna say IT for integral test, okay? That way I don't have to write it. So when you take the integral from 1 to infinity of 1 over x, this is the function corresponding to 1 over n. This is just the limit as b approaches infinity of the integral from 1 to b, 1 over x dx, and this is just the limit as b approaches infinity of the natural log of b minus the natural log of 1, like this, and this is equals to infinity. So because the integral diverges, the series diverges. This is called a harmonic series. So there's a lot of other ways to show that the harmonic series diverges. Using the integral test is probably the easiest way. And I'm gonna show that. So before I continue, this series has the function y equals 1 over x is this function like this. So from 1 to infinity, it positive, decreasing, and has continuous, and 1 over x is the same as 1 over n for positive integers. All right, I'm gonna show that this series converges, and most of the time we will not know what a series converges to, but at least we will know that it converges. So this converges by the integral test. It's like the It movie. No, integral test, because the integral corresponding to the series is the integral of 1 over x squared as x goes from 1 to infinity, and this is the limit as b approaches infinity of the, what is it called, the integral from 1 to b x to the minus 2 dx, and this is the limit as b approaches infinity of minus 1 over x as x goes from 1 to b, and then you plug in the b and the 1, so you get the limit as b approaches infinity minus 1 over b plus 1 over 1, and you get that the integral converges to 1. However, the series 1 over n squared is not equals to 1. In fact, the series 1 over n squared is equals to pi squared divided by 6. This is supposed to be calculus 2, so The reason this is pi squared over 6 is beyond the scope of this book. Is basically when you take advanced calculus, and they use Fourier trigonometric series to show that. So I'm just going to say advanced calculus. But at least we know that the series converges by the integral test, but not to the same value that the integral converges. Okay. Let's do. In fact, so now we have this p series. The sum as n goes from 1 to infinity, 1 over n to the p power, converges whenever p is bigger than 1, and diverges whenever p is less than or equals to 1. So this is by the integral test. Because you just had the integral 1 over x to the p power as x goes from 1 to infinity. And remember this from section 8.8, this was the p integral, which is 1 divided by p minus 1 whenever p is bigger than 1, and this diverges whenever p is less than or equals to 1. Okay, so this harmonic series is a p series with p equals to 1, so that's why it diverges. So this is another way to show that the harmonic series diverges. It's a p series with p equals to 1. And this is a p series 1 over n squared converges, because it's a p series with p equals to 2, which is bigger than 1. This is p equals to 1, so that's why it diverges, and this converges. Alright, I'm going to do one more example of a p series, of a series that we use the integral test. So this series is not a p series. 1 divided by n squared plus 1 is not a p series, but this series also converged by the integral test, because the integral from 1 to infinity of 1 over x squared plus 1 dx, which is the limit as b approaches infinity of the integral from 1 to b of 1 over 1 plus x squared, is equals to the limit as b approaches infinity of tangent inverse of x. And this is the limit as b approaches infinity, tangent inverse of b minus tangent inverse of 1. And this is tangent inverse of b is pi over 2, and then tangent inverse of 1 is pi over 4, and then this is pi over 4. However, so this converges, but not necessarily to pi over 4, okay? So the integral converges to pi over 4, but the series converges to something that we don't know. All we care is that it converges. Okay, I'm going to stop right here for this integral test. Bye-bye.